Welcome, everybody. Good morning, good afternoon, good evening. It is my pleasure to introduce Dahne. Today he's a PhD student at Uppsala University in Sweden. He works on computer-assisted proofs in fluid dynamics and more generally in PDEs. He has results on eigenvalues and eigenfunctions of the Laplacian. And it is a special event today because it's the first time we have a recurring speaker, because Duel already spoke in the CRM Camp Spotlight on graduate research in December, and now he's the first speaker who returns to give another talk in the seminar. Duel, take it away.
Yes, thank you very much for the presentation and for the invitation. As you maybe heard, my cat started sounding as soon as we started the seminar, so hopefully it will not be too problematic. I think it should be fine. Okay, so as you see, I will talk about a computer-assisted counterexample to a conjecture called Payne's nodal line conjecture. And one of the sort of special things about this counterexample would be that it has few holes. So this is joint work with Javier, who's in the audience, and also Kimberly, who is one of his previous students. So it's the three of us who's done this. So as you said, I've been at this seminar once before. So I gave a talk at the CRM Camp Spotlight for Graduate Research, and then I talked about some of my work with Bruno, who's in Lyon. And then I talked about computations of tight enclosures for Laplacian eigenvalues. And the work today will be very much related to this. So the goal is very different, but the tools will be similar. In this case, it was for spherical. We were working on the sphere. So, but today we will work on the plane. So if you attended that talk, you will probably recognize some of the things I will discuss, but the details will be a bit different. So just to begin, get the settings for this. So we will look at eigenfunctions for the Dirichlet Laplacian. So we will have some domain omega, which will be bounded domain and will be planar domain. So compared to in my previous talk where I talked about spherical domains, spherical triangles to be more precise. We have the normal equation for the Laplacian, and we're interested in the eigenfunctions and the eigenvalues. So during this talk, we will be interested in the second eigenvalue, and in particular the second eigenfunction, because these are the ones which are related to Payne's conjecture. So let's get started with this sort of what is it we are dealing with? So what's Payne's conjecture? So it's a conjecture from 1967, and it's sort of very easy to state. It just says that the nodal line of the second eigenfunction, U2, on a bounded domain in R2 must touch the boundary. So remember that the nodal line is the zero set of the eigenfunction. So it says that, and then it's sort of known that this nodal line will indeed be a line, and it says that this nodal line must touch the boundary at least once, usually twice. So an example here, for example, is if you look at L-shaped domain, you compute some approximation of the eigenfunction, it will look like this. So there's one negative part and one positive part, or depending on the sign you choose. And here you see that the nodal line is sort of the line here. And then, I mean, in this case, we see that it does indeed touch the boundary both up here and also down here. So this also was extended to higher dimensional case by Zhao in 1993. So sort of how this would work in higher dimensions. So the conjecture is rather simple. I mean, it's easy to state. It's easy to get a picture of what you're looking for, and it's sort of easy to guess what a counterexample would look like. So it's I mean, it's easy. It would be easy to see that something is a counterexample in some sense, but finding it might be hard. But so the question is rather simple, but it's still been open for a very long time, and in the general case, it is still open. But there have been some partial positive results. So the conjecture has been proved for convex domains, first by Melas in 1992, who proved it for C infinity boundaries. And then Alessandrini in 1994 proved it for general boundaries. So this sort of settles the convex domain case. And in this case, well, then it's true. The conjecture holds. There's also been other authors who proved it under various different symmetries and or convexity assumptions. So that sort of assuming all of these different things, then we can prove that in these cases, well, it will the nodal line will always touch the boundary. So there's some work by Payne himself from 1973, but also other more people here. And this Young and Go, for example, is quite recent, 2013. So there has been sort of ongoing research from this problem for quite some time. So from this conjecture started in 1967, and I mean, some of the more recent results are in 2013. So it's been sort of an interesting thing in this problem for quite a long time. So the problem is then open in the general case, and in particular for simply connected domains. For non-simply connected domains, it's however not true. So a counterexample, which is not simply connected, was constructed by Hoffmann-Ostenhof and Nadirashvili in 1997. So they constructed a counterexample where they took a domain, they showed that there exists a domain for which the nodal line does not touch the boundary. The construction is sort of the construction can be seen in this picture somehow. They start with two circles like this, and then they cut holes in the inner circle. So this would give you a domain which is sort of both the interiors of both of these circles and with these holes. So it's definitely not simply connected. And the nodal line in general will be contained inside this inner circle, but I mean from the beginning it will touch the boundary. But then what they do is that they cut more and more holes in this inner circle, and the more holes they cut, they show using a limiting argument that eventually, when we cut enough holes, then the nodal line will no longer touch the boundary, and it will actually be contained inside here and not touch the boundary. But you have to cut a lot of holes somehow. So this was extended to high dimensions by Fournier in 2001, and also lately, quite recently by Kennedy in 2013. So a similar version of the counterexample works also in these high dimensions. So there's not too much more interesting happening out there, I would say. Or maybe there is, but yeah, the similar counterexample works. So this is nice. Now we know that for non-simply connected domains, the conjecture is not true in general. But they don't give any explicit lower bound on the number of boundary components. So they just use a limiting argument that if we cut enough holes, well, then we're fine. I mean, there's some number of holes for which the nodal line will not touch the boundary. And they say that, I mean, they write in different parts that I mean, this bound would be hard to get, and it's quite large. So some estimates are 10 to the 9, but I think these are only rough estimates. So we have a counterexample, but we don't know how many boundary components it has. So since the conjecture is still believed to be true when you have a simply connected domain, I mean, at least we haven't seen any reason why it shouldn't be. I mean, it's open, but it's believed to be true in some sense. A quite natural question is, what's the smallest number of boundary components for a counterexample? So maybe it is. I mean, maybe there is a counterexample which is simply connected. Well, then N0 would be 1. This is probably not the case. So then you can ask, what is the smallest number? And this question was asked by the Hoffmann-Ostenhofs and Nadirashvili even in their original paper where they gave this counterexample. And their proof doesn't really give a lower bound at all. I mean, they do not have any explicit. They do not get any explicit lower bounds for the number of boundary components, and even if they did, it would probably be a lot higher than what you would need. So this is a natural question to ask, and sort of what can we expect? So we expect it. I mean, definitely there is some n0. It's probably not 1, but how close to 1 is it? That's sort of the question here. And here is where our work comes in. So we prove the following theorem. So we prove that there exists a planar domain which has 6 holes. So n0 would be 7. We have 7 boundary components. And for this domain, the nodal line of the second eigenfunction do not touch the boundary. So this, what we prove in some sense is that, well, n0 is definitely not larger than 7. There is a counterexample with seven boundary components. And the way we do this is that we explicitly give a domain, given here. And then we can compute an approximation of the eigenfunction, which we're given here. So we see that it's sort of negative parts here on the outside and a positive part in the middle. And the white part here would correspond to the nodal line, and it's sort of, at least it looks in this picture that, I mean, it's unclear from this picture if it's touched the boundary or not. You can't really tell. Since the nodal line is what we're most interested in, we can try to highlight this a bit more. So this is a plot of the same eigenfunction, but we plot, in this case, it's the sign of the eigenfunction multiplied by the logarithm of the absolute value. So this is just a nice way to plot it to sort of highlight the nodal line. And we see that we have one sign here, and the nodal line here. From this picture, it's maybe not obvious that it doesn't touch the boundary. So it is very close, but it doesn't touch the boundary. And we will see a picture a bit later on where we see a bit more clearly that it doesn't touch the boundary. But it is very close. And well, sort of the one important part was finding this counterexample. So this is the thing which Javier's students did most of the work for this, for finding that there is a counterexample. Then we had to tune it a bit, but finding the counterexample is one part of the job, which I will not really talk about. But once we have it, we still have to prove that it is indeed a counterexample. And this we do by a computer-assisted proof, then that we construct an approximation of the eigenfunction, we compute rigorous bounds, and prove that the nodal line indeed does not touch the boundary. So here I should maybe note that, I mean, we give a upper bound for n0, which is 7. We do not claim at all that this is a sharp upper bound. So it seems very likely that n0 could be smaller than this. There might very well be counterexamples with fewer holes. We looked a bit for counterexamples with 4 holes, but we're not really able to get it. But maybe if you look a bit more at it, you would be able to find something which works. But we found this one with 6 holes, and that was working at least. Another thing I should mention is that this counterexample is in no way unique. So when looking at this, we found several different counterexamples, or I mean, at least things which looked like they could be counterexamples. So all of these here, for example, here again, it's the plot of the sine times the logarithm of the absolute value. This is the one which is the counterexample, but the other ones here, I mean, they look a bit similar, but they are somewhat different. But here, for all of these, it looks like the nodal line do not touch the boundary. Why did we end up choosing this one? I mean, for example, here it looks like it's actually bigger distance between these two than it is here. So maybe you think that this is a better choice. I guess there's 2 reasons we chose this one. One was that the numbers looked a bit better. So it looked like we had to get we didn't have to get quite as accurate error bounds, but also that we managed to get a good convergence when we were computing the approximation. So it was hard to deal with this sort of thin things we have here. It was hard to get good approximation for the eigenfunction in this case. It was a lot. We got a lot better results when we had this sort of more regular triangles in some sense. Yes. So when we have this domain, we want to construct this counterexample, and it's sort of done in 3 steps. So the first step is that we need to find a good numerical approximation, which we will call u2 tilde of the eigenfunction and lambda2 tilde of the eigenfunction of the eigenvalue. So this we need to find in some way, but it can be non-rigorous. We need a good numerical approximation. it will look like this. Then we need to compute rigorous error bounds for this approximation. So we will need both error bounds for the eigenvalue. So we'll get some enclosure which we prove contain the eigenvalue. But we will also need L infinity bounds. So since we want to prove something about the nodal line, we need to sort of evaluate the eigenfunctions. We need L infinity bounds as well. And this we will also be able to get. Another important part, which is a quite large part of the proof, is that we need to certify that the approximation we have indeed corresponds to the second eigenfunction, that the index is the correct one. So that's part of the conjecture. So in the second step, when we compute error bounds for our approximation, they do not tell us anything about the index. So we need to use some other methods to certify that our approximation indeed corresponds to the second eigenvalue. And this is actually most of the work is in this part, let's say. So the procedures 1 and 2 here, where we find approximation and compute error bounds, this is very similar to the work I did with Bruno, which I presented in the last seminar. Then we were working on the sphere, now we're working on the plane, but a lot of the methods are similar. And all three of these are actually similar to what Javier did with another student of Gerard, also wrote a paper about this last year. So they also dealt with this type of problems, and they also did all three of these. And in fact, the certification of the index is very much very similar to what they do. A somewhat big, I mean, the biggest difference you could maybe say is that in both of these cases, they were working with triangles. So here it's spherical triangles. They were working with triangles in the plane. So it's sort of very simple domains. Whereas in our case, we have a much more complicated domain, which is not simply connected, for example. So that the domain is more complicated was one of the main issues to deal with. Another issue to deal with, I guess we will come to that on the next slide. But yeah, so the procedure is heavily based on these two. So let's start with this determination of the index. So this is sort of the most one of the more important parts. So just to get some idea of what's happening, we can compute sort of approximate eigenvalues. So this was basically just throw in the domain to MATLAB and see what it gave. So these are rough estimates. I mean, they're not rigorous in any way. We're interested in second eigenvalue, and there's two things to notice here. One is that it's very close between the second and the third. So you see between these two, we have quite a bit of distance, but here it's a lot closer, and this will lead to some complications. Also, the third and fourth eigenvalue seems to be a double eigenvalue. I mean, these are numerics, so it's not for certain, but at least they are tightly clustered, and this is also complicated to deal with. So there are different methods for determining index in the sense that we need to do. One very nice way is to work with homotopy methods, like those used by Plum, for example. And they usually work very nice when you can use them. But in our case, our domain is very far from any domain where we know the eigenvalues. So it would be hard to do some sort of homotopy method because we needed a starting domain where we know the eigenvalues exactly. And in our case, we don't have that. So it would be hard to work with these methods. Instead, we do the same method as Javier and Gerard did in their paper. So we're basically following what they did. And it's in two steps. So the first step is that we separate the first 4 eigenvalues by computing a lower bound for lambda 5. So we'll compute a lower bound for this eigenvalue, which means that we know that the only eigenvalues which are lower than this lower bound are these 4. So once we've done that, we will isolate these first 4 eigenvalues, so we can know the index of them. So this will be complicated by the fact that there is a double eigenvalue, or at least a very clustered eigenvalue. So we'll have to deal with that as well. We can maybe notice here as well that if we would have had a bigger difference between these two, then we could maybe have lower bounded lambda 3 using the method we will use here directly. But in this case, this lower bound is quite rough, so it would not give good enough bounds for lambda 3. Or at least not in the, yeah, you would have very hard time to get good enough bounds. So that's why we do the lower bound for lambda 5, where there is some distance, and then we handle the 4 often. So this first part is about lower bound in the lambda 5. And the main tool for this is we're basically using a finite element method, but we need rigorous bounds. So the main tool for this is a theorem by Lee from 2015. So if you have a polygonal domain, which we have, with a triangulation, so that each triangle has a diameter as most h. So here is a triangulation of the domain, which very small triangles, which you can hardly see. Then if you look at the kth eigenvalue of the Laplacian on this domain, lambda k, and then you let lambda hk be the kth eigenvalue of the sort of corresponding Raviat discretize problem. So this is basically the finite element problem in this domain. So this will be the eigenvalue of a matrix. Then this theorem, what it tells us is that we can lower bound lambda k by this, and this ch here is an explicit constant. So there's also some more related works to this. So we want a lower bound for lambda 5. So we have this, and since this is monotonic in lambda h5, it's enough for us to find a lower bound for lambda h5. So once we have that, we get a lower bound for lambda 5, which is what we need. So how do we compute this lambda h5? Well, so it's, as I said, it's basically a finite element variation of the problem. So you rewrite the problem in a weak formulation. You get something similar to this. Here you define a stiffness matrix and a mass matrix, A and B. And then the problem reduces to computing this. So A times X is equal to lambda BX. In our case, B turns out happens to be diagonal, so it's very easy to invert. And we can easily rewrite this as mx is equal to lambda x. So lambda h5 is just the 5th eigenvalue of this matrix M. So this is a rather explicit matrix, or it's an explicit matrix. We can compute all the elements in it. The main issue is that it's rather large. So we need a somewhat fine grid for doing this. So the matrix is of size 6,000 by 6,000. However, the matrix is sparse. In our case, it even has rational components. This is not important for what we do with it, but it sort of means that it's easy to compute it. So getting M is easy. But now we need to lower bound the 5th eigenvalue of this matrix, and it's a large matrix. So the procedure for computing the lower bound of the 5th eigenvalue of this matrix will be as follows. So we will construct an almost diagonal matrix D. So it will not be quite diagonal, but sort of numerically it will be diagonal, is the idea, I guess, which is similar to, so it has the same eigenvalues as our matrix M. So we can reduce the problem to lower bounding the 5th eigenvalue of this matrix D. And then we will bound the eigenvalues of D using Gershgorin's generalized disk theorem. So this is the procedure we will use for getting this lower bound. So for the first part of constructing the matrix D, we will make use of a lemma, but let me get back to that shortly. So if we have Q tilde be a matrix with columns forming a sort of numerical approximate of a normal basis of eigenvectors of M. So we just compute the eigenvectors using any numerical routine, giving us some approximation. Then the matrix D tilde, given by as Q tilde transpose times M times Q tilde, will be almost diagonal up to sort of numerical errors in some sense. It will not be exactly similar to M because Q tilde is only an approximation, but it will be sort of approximately similar to M. So the eigenvalues will be similar, but not exactly the same. So to handle this approximately similar, we need something which is exactly similar. this is what we use this lemma for. So it says that if we have a number of vectors in Rm, and there is some s greater than 0, so that this inequality holds. So this means that, I mean, if they are exactly orthonormal, then this would be then s would be 0. So then all of these would be exactly equal to 0. But now we have an approximation, so it will not be exactly orthonormal, but up to some error, and this error is s. So s is somehow small. Then there exists an orthonormal set of vectors which is close to vi. So given bounded by this square root of 3s. So if s is small, then we know that there's an orthonormal set of vectors close to our set. So using this lemma, we see that there is a Q which is orthonormal, which has orthonormal vectors, and which is close to this Q tilde. So we can get the errors by this inequality. And then we can get that D is equal to Q tilde MQ. It will be still not exactly diagonal, it's only almost diagonal, but it's now exactly similar. So it is similar. But we don't have this Q explicitly. I mean, we only have, it's just, we know that there is a Q close to Q tilde. Yes. So we don't know D explicitly. We only know D tilde. But using this lemma, we can get the upper bounds for this difference. So you do some computations, and then you end up that you get some sort of upper bound, and we can see that S occurs in both of these terms. So as long as S is small, that our approximation was approximately orthonormal, we will get that this bound is small. So we have a good approximation. And here is where we use the Gershgorin's generalized disk theorem, where that kicks in. So we'll let Ri so will be the radius of the disk. So it's just the sum of all the off-diagonal entries on the ith row. So I mean, our matrix will be almost diagonal, sort of numerically it will be diagonal in some sense. So this is expected to be small. So Ri is supposedly small if we have a good approximation. And then we look at the disks given by just the diagonal entry, and then plus minus this radius. So basically it will be as, I mean, the idea is that, I mean, if we have an exactly diagonal matrix, then the diagonal element is the eigenvalue, and the radius will be 0. So we have the eigenvalue exactly. But in this case, we will have the diagonal element will be almost equal to the eigenvalue plus some error. And this is given by the sum of the diagonal entries. And then using the Gershgorin's generalized disk theorem, we have that, so in our case, that if the union of the first 4 disks and then intersected with the union of the remaining disks is the empty set, then this theorem tells us that this first union contains exactly 4 eigenvalues, and the second union contains exactly n minus 4 eigenvalues. In particular, this means that the 5th eigenvalue must lie in this union, and the lower bound for this union gives us a lower bound for the 5th eigenvalue. So we can do all of these computations, and we end up with, we find that these 2 unions have an empty intersection. We look at the lower bound for this union, and then we get this number. So we get some lower bound for lambda 5h. And then we can use the Lluís theorem, which then gave us a lower bound for lambda 5. So we get this lower bound for lambda 5. And if you happen to recall the values for lambda 4, this is larger than the approximate value we had for lambda 4. So it will work. It's sort of good enough. But if we did it for lambda 3, for example, we would get a lower bound which is smaller than lambda 2. So then it would not work. But here it works. So then we have the lower bound for lambda 5. So then the next part is that we need to isolate the 4 eigenvalues which we know exist below here. Or we know that there at most 4 eigenvalues below this lower bound for lambda 5. So we need to find them and isolate them so we can determine their indices. And this is done by, we construct 4 approximate eigenfunctions, so 1 for each eigenvalue. Then we can use this, some other machinery to compute these enclosures of these eigenvalues. So this will give us some enclosure of the eigenvalue, some enclosures of these 4 eigenvalues. So up to here, we don't know the index. So we don't know that this is actually is the first one, this is the second, this is the third, this is the fourth. So we don't know that sort of a priori, but we can compute enclosures of them, please. And what we get then is that there is an eigenvalue in this interval. So this corresponds to the enclosure of that. There is an eigenvalue in this interval corresponding to the enclosure of that. And there is an eigenvalue in this interval corresponding to the enclosure of that. But this also happens to be not exactly, but almost the same as the enclosure for this one. So there's one eigenvalue here, one eigenvalue here. Supposedly there's 2 eigenvalues here, but this we will have to prove. But assuming that we do prove that there are 2 eigenvalues here, then we know that there's 1 here, 2 here. And there's only 4 below this line. Oops. There's only 4 below this. So then we know that we have found them all, and we know that this must be the second one. So as long as we can prove that we have this eigenvalue here, and 2 eigenvalues here, then we're done. We know that the index of this eigenvalue is the second one, which is what we need. Yes. So before we can do this, we need these approximations. We need to compute U1 tilde, U2 tilde, U3 tilde, and U4 tilde. And here the method is also the same as in both my previous paper and Javier's previous paper. We use the method of particular solutions. So I will be rather brief with how this method works. So you can look at my previous talk, I guess, if you want to see this, but also look in the paper. But it was introduced by Fox and Richard Moller in 1967, and it has been improved by Batke and Trevethan in 2005 in their paper Reviving the Method of Particular Solutions. And what the method does is it helps you to find approximate solutions, lambda tilde and U tilde, which solves this equation. So they are exact eigenvalues in the sense that they solve they solve this equation exactly. However, they are not necessarily 0 on the boundary, so they are not true eigenfunctions, because then we would require that they are 0 on the boundary as well. But they are approximately 0 on the boundary. So it's important that they satisfy this equation exactly, but this equation only approximately. And the idea of the method is that you look at linear combinations. You have some basis functions, so phi I, which do satisfy this equation exactly. So these you have to sort of know beforehand. And in many cases we do. So these are sort of known beforehand, known basis functions. And then we look at approximations which has linear combinations of these. And we try to choose the linear combination so that it's small on the boundary. And sort of what this method tells you is how to do this in a good way, which is something I will not really go into detail with. But it turns out that the choice of basic functions, how you choose these basis functions in your series, is very important if you want to get good, which in this case means root exponential convergence. So we combined ideas from both Fox and Rich's and Moller's original paper, Batke and Trevethan's paper where we revive it, but also notably a much later paper by Trevethan as well, which is about solving Laplace problems with corner singularities via rational functions. And here we introduce something which they call the lightning method. This method is very important for how we choose our basis functions. And it's also very similar to what we're doing in here, in these 2 papers. So between these 2 is sort of how we, the inspiration comes from these 2, but we have done sort of, we have had to combine these in different ways. So here is a sort of rough sketch what it looks like. So we have 3 types of basis functions. It's the type 1 basic functions, I call them. It's sort of the ones in the original MBS article. They are just Bessel functions with an alpha here. And they are the ones that is outer vertices. And the alpha here corresponds to the angle of the vertex. So they are chosen in a way so that they are identically equal to 0 on, so for example, for the expansion here, it's identically equal to 0 on this line and identically equal to 0 on this line. So it sort of satisfies the boundary conditions on 2 of the lines from the start, which is good. It makes it a lot easier to deal with. So we have this type of expansions from all of the outer vertices. However, for these vertices, we do not use them, and one reason is that they have a branch cut to the alpha, which means that you can't really use them if we would have this type of expansion here, you would have to introduce a branch cut somewhere. So you couldn't really get a continuous eigenfunction. You would need to have a branch cut. So they don't really work in this sort of interior vertices. Instead of these vertices, we use these lightning charges, which are introduced by Trevelyan in his paper. So they are the ones we use to get good convergence around these vertices. And then we have an interior expansion, which just is this inner point, which sort of helps even out things sort of on the global scale, whereas the rest of them mostly take care of boundary values. So that's sort of the basic functions we choose. And one important part, which is sort of what makes it actually work in the end, is that we make use of the symmetries of the eigenfunction. So we know that we expect the eigenfunction to have a 6-fold symmetry. So what we do is that we sort of enforce this in our choice of basis. So we'll actually, so for example, we have these 6 expansions from these 6 corners. We will force them to have the same coefficient. So we expect them to be symmetric, have a 6-fold symmetry, so that they should all be the same. And we actually enforce this in the expansion. So we take them sort of all of these 6 as one term in the expansion, which greatly reduces the computational cost because we get a lot fewer coefficients to have to deal with. And this is why it's sort of actually it's possible to do all of these computations. Yes. So what do we get in the end from this? So we need to compute the approximations for 4 different eigenfunctions. So we have U1 tilde, U2 tilde, U3 tilde, and U4 tilde. The approximate eigenvalues we get for the different ones are is this, 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 and this. These 3 are just the approximations we took from whatever MATLAB gave us. For U2, we worked a little bit harder and found a slightly better approximation. Not all of these digits are correct, definitely not, but it's sort of we took this approximation as the starting point. And we need very different amount of accuracy for them. So for the first one, we don't really need any accuracy at all. We just need to get an enclosure for this first eigenvalue, which is very far away from the others. So here we can use very few coefficients and hence very few collocation points. So it's sort of very cheap to compute this. So it gives us this eigenfunction. So this is a somewhat, I mean, this is not the best, this is not a super good approximation, but it's good enough for what we need. For the second eigenfunction, this is the one where we need the most accuracy, because here's where we also have to deal with the nodal line. So here we need to use a lot more coefficients and compute for a lot longer. And finally, the third and the fourth, we see that they have quite different symmetry. Here we need good accuracy, not because we have any nodal line or something we have to deal with, but because they are very close to this eigenvalue. So as you see, they're quite close to each other. So we need somewhat good enclosures for these so that they don't sort of cover these ones. So that's why we need a bit more work on these as well. So then we have these approximations. So we compute these 4 approximations. And here it should be noted that so far we have not certified these indices. So this is just, I mean, it's sort of obvious that this is the first one, and it's obvious that this is the second one. And I mean, here I guess you can choose the order, but it's sort of obvious that this is the third and fourth one. But there's no proof of it yet. I mean, it's just non-rigorous. We can see this non-rigorously. but we will need to prove this in the end. So given these approximations, we need to compute rigorous error bounds. And the main tool for this is the following theorem by Moller and Payne. So this is a slightly later paper than the one by Fox and Rich and Moller, where they introduced the method of particular solutions. So this is a slightly later paper by at least some of the same people, where they give a way to compute these bounds. So given an approximate eigenpair, lambda tilde and u tilde, and approximate in this case means that it solves the differential equation exactly, but it's not necessarily identically equal to 0 on the boundary. So it's almost equal to 0 on the boundary, but not. It's not necessarily. Yeah, it has to solve the differential equation exactly. Is the important part. Then we compute the value of mu. So it's just something depending on the area of the domain. But the important part is mainly that we compute the supremum of this approximation on the boundary. So if it's a good approximation, then it would be almost 0 on the boundary. So this supremum would be small. So the better approximation we have, the smaller this supremum is. And then we have to normalize this somehow by the norm of u tilde. So computing mu is maybe non-trivial. I mean, we have to bound these functions on the boundary. It's not too complicated, but requires some work because there's a lot of cancellations in this series. Computing this norm also requires some work. But I will not talk about this too much unless I happen to get more time in the end. But at least mu is we can compute a bounds from mu. This is the important part. Upper bounds in particular. So what the theorem says then is that then there exists an eigenpair lambda k uk, satisfying that lambda tilde minus lambda divided by lambda is less than or equal to mu. So if mu is small, we get that there's a lambda very close. Oh, there should be a lambda k here, I guess. We get that. Sorry. We get that there's an eigenvalue close to this. But notice that it doesn't say anything about the index. It also gives us L infinity bounds with this slightly more complicated formula. So we get explicit bounds for this. There's two annoying parts in this formula. There's this g of x and it's this alpha. G of x is just here g is the Green's function, so you need to compute this thing, and you can in the literature you can find an upper bound for this, which is given by this. So we use this upper bound as a sort of the upper bound to g. Maybe more annoying is this alpha. So alpha is the distance from our approximate lambda to the other nearest eigenvalue, which is not lambda k. So if there are two eigenvalues very close to each other, then alpha will be very, very small, which means that since we divide by it, this bound will be very, very large. So if two eigenvalues are close to each other, then alpha will be small. In particular, if we when we have a double eigenvalue, this becomes even more complicated, which I will also get back to. But at least we can use this theorem to compute bounds for lambda. So here we don't need alpha or anything like this. We just compute this mu. So we get that, well, mu is smaller than or equal to 0.14 in this one. So it's quite large. I mean, and the enclosure we get is quite large, but good enough so that it doesn't contain this. Here we get a quite narrow enclosure, and for these two we get sort of ish narrow enclosures. They are not too bad at least. The important part is that this one is clearly separated from the others, and these two is separated from this one. So we have one eigenfunction here, one eigenfunction here, or one eigenvalue here, one eigenvalue here, and at least one eigenvalue here. We will have to prove that it's 2. So now we're closer to proving the index. We just have to handle that. We need that to prove that there's 2 eigenvalues here. Okay. So how should we handle this double eigenvalue? So we want to prove that u3 tilde and u4 tilde corresponds to 2 different eigenfunctions, so that they're not approximations of the same eigenfunction. I mean, numerically, this is obvious. So, I mean, these are definitely not linearly independent of each other. So numerically, it's obvious, but we still need to prove it rigorously. Yes. So assume that U3 tilde corresponds to UK and U4 tilde corresponds to UL. We want to prove that K is not equal to L. So it would be enough to prove that the quotient on two different points are not the same, because then they cannot be linearly dependent. So this would be enough if we could prove. However, we don't have a lower bound for alpha. So remember that to get this L infinity bounds, we need a lower bound for alpha, which we don't have because, I mean, it's a double eigenvalue, but so we don't get any lower bound for alpha. So we get no upper bound for the error, which means that we can't prove this directly. So we will revise the goal slightly. We will prove a slightly weaker statement. We will prove that there are two eigenvalues in an interval given by this, which is slightly larger than the union of the enclosures of the two eigenvalues. So it's slightly larger, but not a lot larger. And the way we prove this is by contradiction. So we assume that there's only one eigenvalue in lambda prime, and we will prove a contradiction by this. So if there's only one eigenvalue in lambda prime, well, then we get the lower bound for alpha, because we know that, for example, for this eigenfunction, we see that if there's no eigenvalue in here, well, if there's only one eigenvalue in here, it must be the one which is in here. And then we know that the distance to the closest other eigenvalue is at least the distance between the difference between these two radiuses. So we get the lower bound for alpha for both of these cases. So that's why we need this to be slightly larger. And then we can prove that this doesn't hold, so that they are not linearly dependent, which means that they must correspond to different eigenvalues, which means we have a contradiction. So this means that K cannot be equal to L, which gives us this contradiction. But notice that we don't actually prove that K is not equal to L. I mean, so we only prove that there cannot be an eigenvalue. There cannot be only one eigenvalue in this interval. We don't prove that there has to be two in this. So it's not important for what we need. We only need to prove that there's two eigenvalues in this interval, but we don't actually prove. We don't prove that these do not correspond to the same eigenfunction. But it's also not something we need. So now we have done the main part of the work, this isolating lambda 2. So we have this lower bound for lambda 5, lambda 1 is here. There's at least two eigenfunctions in this interval, which is now slightly larger than the one we had before. And lambda 2 is in here. So we know that this must be the second one. We also get this lower bound for alpha, which we needed for getting the L infinity bounds, because we know that the closest eigenvalue, so if our approximation is there in the middle, then the closest eigenvalue is here. So we get this as the lower bound for alpha, which then gives us these L infinity bounds. So then we go on and prove that this second eigenfunction indeed has an isolated nodal line. And we do this in two steps. We first prove that U2 is strictly negative on this gamma here. So this gamma sort of goes around this whole blue thing, and we prove that the eigenfunction is strictly negative on this. Then we prove, so in the blue thing it's positive. Then we prove that there is a positive point inside here. So indeed it is positive somewhere in here. This means that since it's positive somewhere in here, and it's negative on this whole thing, it needs to change sign somewhere in there. So it needs to change the sign somewhere. So the nodal line must at least partially be in here. But since it's strictly negative on this whole thing, the nodal line can't cross this gamma. So the nodal line must be fully contained inside this gamma, as we see here. This part is rather straightforward. We have this, we prove that U2 tilde, our approximation, is less than or equal to this number on gamma. I mean, we have our approximation, we can just compute the maximum, or the maximum on this gamma. It's not too hard. And then we just check that our L infinity bounds for U2 tilde is smaller than that. So notice that the absolute value of this is smaller than the absolute value of that. So U2 tilde must certainly be negative as well. Proving that it's positive on a point inside gamma, it's, I mean, even simpler. We just take a random point inside. We get this value. Well, the L infinity bounds are certainly smaller than this. So U2 must certainly be positive on this point as well. So the conclusion from this is that indeed the nodal line is fully contained inside of gamma, and hence it cannot touch the boundary. And then we have the proof. So that's sort of, that's the end of it. So before I end, I just want to give some more computational details maybe. So I can mention that all the code for this is written in Julia. We use ARB for all the rigorous computations through both Nemo and arblib, which are two interfaces for ARB in Julia. The lower bound of lambda 5h was actually the most time-consuming part because the matrix is very big. It took 30 hours to compute the approximation of Q tilde, and it took 2 hours for the verification later on in ARB. Computing the approximate eigenfunctions was only 10 seconds for U1 tilde. U2 tilde, where we needed the most precision, took 6 hours, whereas U2 and U3, oh, this should be U3 and U4, took only 5 minutes each. Computation of rigorous bounds were actually very similar to the computation of the approximation. 10 seconds in this case, 6 hours in this case, and then 30 minutes in this case. And then the proof that the nodal line is contained inside of this gamma was very quick, I think, a few minutes only. So finally, if you're interested, all the source code as well as notebooks showing all the proofs are available on my GitHub page, I guess it is. So here you can find both all the code and you can also find notebooks, both. So there are Pluto notebooks which you can run through Julia, but they have also been exported to HTML, so you can look at the sort of the actual evaluation of the code there as well for all parts of the proof. So that was all. Thank you very much for listening.
Thank you very much, Joel, for this very nice talk. Are there any questions?
Yeah, actually, I have several questions.
Yes.
Michael, go ahead.
So the first one is, you said that my homotopy method is a bit hard or is hard to apply, and I don't quite agree with that. So actually, you can. So this domain looks a little bit far from any domain with known eigenvalues, but you can, for example, you can at the first step you could get a homotopy from a surrounding rectangle to this hexagon, right? Without the holes in it first, right?
Yeah.
And so by that you can get rather easy enclosures for the hexagon, and then you just just pop up these little holes in the middle. So because there is the points, when you let them grow from a point, then the points have capacity 0, so you can easily continue the homotopy by popping in little triangles inside. So that means you have, you understand what I mean?
Yeah, I understand what you mean. Yeah, I guess we didn't think, I've never seen it before when the holes popping up, so I guess that's one of the reasons we didn't think about it.
But that should be an easy, in a sense, an easy homotopy, right? So I would guess you need something about 2 steps from the surrounding rectangle to the hexagon, and then maybe.
Yeah, and the hexagon should be trivial handle, I think, as well.
Yeah, that's well, but then just insert little holes. Maybe you have perhaps you can even enclose the let pop up the holes in the full size already. But if not, you can make them first a little bit smaller and then let them grow, right?
Okay.
But my rough guess would be that it's not more than 10 homotopy steps. So it is not so complicated, I think.
Okay. Yeah, this would be interesting to try them. Yeah.
And it would solve a lot of other problems. So it would solve the problem of getting a lower bound for alpha, for example, right? So you don't.
Yes. Yeah. Then we only really have to compute U2. Exactly.
That's right. So in my opinion, but okay, maybe I'm a bit biased.
No, I agree. I mean, it would definitely help. I mean, this is the hardest part of the proof somehow. I mean, to get this index, and if we can do this somewhat easy with the homotopy method, this would be excellent.
So I have more questions, but I can wait for others if you, Jean Bauer, if you want to.
Yeah.
May I ask a question?
Yes.
First of all, why didn't you use a pentagon? Why did you use a hexagon?
I think the main reason.
The idea is you have a problem with double eigenvalue, and as far as I see, it arises from a lot of symmetry.
Yes.
And
but the symmetry also helps. So
I see. And the second question, it's basically just a remark. I had a kind of direct chat to how do I pronounce that name? Javier. I had direct chat with Javier, and I suppose you can basically prove that U3 and U4 belong to the same eigenvalue. Basically, if you take U3 rotated by 60 degrees and average it with unrotated function, then it should have a nodal line which goes from mid-edge to mid-edge. I think it should be possible to prove it like that.
Yes, so I think you're right. I mean, I think it's definitely possible to prove that it's double eigenvalue. So we discussed some other, when we were writing the paper, we discussed some other methods of proving this, and we came up with another method which I think also proves that it is a double eigenvalue. But in the end, it ended up that we needed to write slightly more code. So we ended up not using it. So the nice thing with this was that we could use all the same bounds we used for everything else.
I don't think you need to code to prove it. I don't think you need to code to prove it.
Okay, then I would have to think more about it.
Well, the point is we don't need it to be an eigenvalue. We don't care. We just want to split it from lambda 2.
Which is a good answer. Thank you.
And also going to the question of the pentagon, if you try it with a pentagon, then it's not so easy to find a closed nodal line, to find a counterexample or at least a candidate. Like Joel showed it and it looked easy, but it's not so easy to find all these shapes where the nodal line is closed. This is very sensitive to the numerics.
If you move them very, very small amount, they will fail somehow. But another important part is that we have a lot of symmetries here. So the pentagon, I think, would actually be harder to compute approximations for because we lose a lot of symmetries.
I see. Thank you.
Thank you. So, okay, well, Maxime, go ahead.
Yeah. So I have a maybe naive question. When you have this matrix M, like 6,000 by 6,000 something, and you want the lower bound for the fifth eigenvalue, is it completely hopeless to just brute force that and enclose all the eigenvalues? I mean, if you were to use MATLAB, for instance, IntLab does that. I don't know if this, maybe the matrix is too big in practice. I'm not sure, but it does. I don't know if it's completely hopeless or if you wanted something more elegant because you don't need all the eigenvalues. So
I tried to. So ARB has a method as well for computing eigenvalues of functions of matrices, and I tried to give it to that, but I gave it a few hours, but it didn't return. So I sort of gave up. My guess that it would take a long time. 6,000 by 6,000 is quite large. So my guess is that it would take too long time, but I don't know. I have not tried it with IntLab, so I don't know how well it would handle it. I think there are more clean way of doing it than we do. So I don't think we do it in the cleanest way. I think there are definitely better ways to do this. We do not use the sparsity, for example, at all. So I think there would be nicer ways to do it, but in the end, it ended up all right. It worked. So.
Yeah, just out of curiosity, I mean,
Yep.
I like it the way you did it, actually. So.
I should say that maybe when you add it that this 30 hours is quite bad. I mean, so actually it's only because of some slight complications it takes 30 hours. If you just give it to MATLAB or Julia, I think it takes around 10 minutes to get an approximation. We just happen to need slightly more than double precision, which and some other reasons why it takes 30 hours. But yeah, IntLab would I would actually be interested to see how IntLab handles this matrix. That would be nice to know.
Yeah, I've never tried with a matrix so large. That's why I'm asking.
No, it takes around 30 gigabytes of memory, so I can't even do it on my normal laptop. So it's one of the issues. Oh, I think it's okay, but that's because it's an ARB. It's around 6 gigabytes, I think, the matrix in ARB. So all the computations uses a lot of memory.
Okay, thanks.
Thank you.
Hiroshi, do you want to ask your question or because you ask a question in the chat?
Yeah, I ask you, is this number 7 the minimum number of the boundary of your program?
Most likely not. So I would guess that you can, my guess, pick up some sort of this version, is that you could go down to 4 boundaries. But this is then you can do sort of similar construction that you have 4 boundaries and then have these things around the vertices. My guess is that you could get something like this, but we didn't manage to. So I don't think this is the minimum. I would be very surprised if it is.
The other question is, you could separate the eigenvalues by using the Sturm counting method in approximate calculation. Your generalized eigenvalue problem A and B is a matrix. A minus lambda B is, for example, Koreski decomposition. You get signatures of the.
You mean for the matrix? You mean?
Yeah.
Yes. Yes, I think this was one of the things we started looking at towards the end, when we realized that it would take a long time to do the matrix, do it the way we did now. But then the computations finished before we continue looking. But yes, I think this is one of the things we looked at as an alternative.
This will take even longer. Like I've tried this before for other programs, and this took longer.
Can I ask a question about the final step where you prove that the nodal line does not touch the boundary? Can you show that picture again with the curve gamma?
Yes, this one.
Yes, this one. So how do you know that there is not an additional nodal line close to one of these little triangles, right? So there could be a nodal line just coming out of that little triangle and immediately going back. So quite close to the whole boundary, there could be a nodal line. How can you exclude that?
So that's using Courant's nodal line theorem. It tells us that there is at most one. So we know that there's at most. This I should have mentioned as well.
Okay.
So we only need to prove that there is one nodal line inside here, and we're done.
All right.
So yes, that's important. Thank you.
I have another question concerning the numerical approximations which you computed by the particular solutions and then collocation on the boundary. So why do you not use a simple finite element method so a standard finite element method for computing all approximations?
So at least well, one of the reasons I guess is that I worked with this method of particular solutions before. So that's one reason, and it was good for giving very high precision results. I guess, I mean, for example, when we tried to plug it into the MATLAB solver, which is how we did sort of the first few computations, we had to use extremely fine meshes to get anything which resembled a good approximation. So my guess is that it would be hard to get a sufficiently good approximation. We need, I mean, quite good L-infinity bounds. But I would say I'm too unfamiliar with finite element methods in general to be able to say if how hard this would be, because I've not worked with them too much.
You think that this method could be more would be more accurate? At least that's what you're expecting.
So yeah. So this is what Trevisan usually says as well. That it's good for medium to high precision computations. Finite element methods is good for low precision computations. But my experience with it is too small to be able to say more.
Depends of course which elements you take. Anyway.
Yes.
So
yes.
by the way, this L-infinity bound which you use here, you can also go via H2 bounds and then Sobolev embedding, explicit Sobolev embedding from H2 into the space of continuous functions. I also gave explicit embedding constant for that embedding. I didn't compare it with this approach with the alpha and the G, which is the integral of the Green's function squared. And there's also rather rough estimate in there, but when you go via embeddings, it may be more accurate. So the L-infinity bound might be better, but I cannot claim that, but at least look at that.
So no, we looked at other type of bounds, but in most cases we didn't find explicit constants, which would work in our case. But if you have one with explicit constants, I think maybe if we just missed it, or if you did you look at this?
So I have constants for the full H2 into this space of continuous functions for the full. So you don't need the domain, so to say. So the domain it's not so important so much.
Yeah, but then that's a problem, right? You have to see the domain for like the constant to be a good constant.
Once again,
that the constant should depend on the domain.
Yes, of course.
So if you get a universal constant, then it's probably not very
good. No, that's not universal. Of course, it depends on the domain. But what I want to say is that it depends on the domain in a rather harmless way, right? So it's easy to compute. You have just to compute integrals over well-known functions over the domain. And,
yeah, so you have to do quite some work to get the constants or to get a reasonably good constant. Whereas in our case, the constant was almost for free.
Yeah, but, okay.
And I think this was the main reason.
It may be it is for free, but it may be worse. That's what I'm not claiming that.
Yeah, it might definitely be. And I think, I mean, in particular, this this g of x here will tend to 0 close to the boundary. So this is a terrible bound.
Yeah, that's precisely, and that I think that could be avoided by explicit embedding. But I'm not sure. Of course, the bounds in this explicit embedding are also not optimal, right? So we cannot there will be.
Yeah, and fixing this would help quite a bit, since where we need the L-infinite bounds is really very close to the boundary. So this is actually a quite big drawback of the bounds we're using, definitely.
Can I ask a question? So I understand that you don't need that the eigenvalue is a double eigenvalue, but wouldn't it help you to know that it is a double eigenvalue? Because then you only need to show that there's one, because then you know that there's the other one.
But
wouldn't it help you?
If we did it, it would be fine as well. But I mean, to do that, most likely we need to compute two eigenfunctions anyway, two approximate eigenfunctions which are different. And I mean, once we've done that, then the rest for us is sort of direct.
But then they would be related by some symmetry operation, right? If there's a double eigenvalue, so you don't need to. Yeah, I mean, it should be a symmetry argument, not an argument that needs a lot of computations, right?
Maybe not.
I'm just asking. Yeah, so wouldn't it help you if you know? Because then you only need to show that there's one, and it seemed to be that you had to do quite a bit of work, at least in what you explained, to show that there were in fact two, even though it might not take a lot of time.
If we knew that there were a double eigenvalue, yes, then we would have only need to compute one of them. Exactly. So that would help. Yes.
But in reality, the biggest part of the work is for U2. Like U2 is the difficult thing to compute, not U1 or U3.
Yes. Okay. No. I appreciate that. I understand. Yeah. Other questions?
I have an additional one concerning the beginning of the whole story. You showed this Hoffmann-Ostenhof, this theoretical construction. What I couldn't quite recognize from your drawing, and actually I don't know the paper, are these little holes made into a circle, or is that something which has positive measure? These things in the middle which remain there, these little black pieces.
They have positive measure, so you cut explicit holes. So they have a positive measure.
But what I mean is this still a circle with holes, or is that a fat ring with holes?
It's a circle with holes, I think. Yes.
Okay. Then actually, I think you have you could add to your list of what you have proved one more thing, namely you proved that there exists a Lipschitz domain where there is a counterexample, because the Hoffmann-Ostenhof domain is not a Lipschitz domain when it is just a circle with holes. Right?
Yes, that's true, I guess.
So it's not a Lipschitz domain, and you not only gave a few holes, but you also provided a Lipschitz domain where the counterexample can be given.
Yes, that could be true. Now I'm not entirely sure how it was in their case, but I think it's a circle. So I think that's true.
Yeah, a Lipschitz domain is also a nice result that you can prove it. Get a Lipschitz domain example, not just this less regular domain which they had. Okay, thanks.
Hi, can I ask a question?
Yes.
Yeah, first of all, I would like to thank you for the nice talk. It's very nice. So, and my question was probably not the question, it's kind of a suggestion, perhaps in the continuation of question which was asked by Sergei Kolonitsky. It's basically the following one. So what about if you will treat or maybe consider the third eigenvalue in your domain as the first eigenvalue on the half of your domain?
Yes, so this was exactly the approach we were thinking about. So this actually, if you read the paper, there's a remark about exactly this approach. So this was what we were trying to do, but so exactly, I can go to the picture. I even have a slide for it, which I didn't use in the end. So exactly, if we split this in two, we have that this is a simple eigenfunction here. Split it into here. This is a simple eigenfunction up here, and then we can prove that they indeed are different eigenfunctions. That's true. In the end, we needed to write slightly more code for doing that than in the way we did it now. So that's why. But it's a good observation.
Okay, thanks.
Any remaining questions? We already grilled Joel for 20 minutes, so it is also okay if that's if we stop there. Huh? But if there are any lingering questions, then no. If not, then let's thank Joel again for a great talk. That also drew a lot of questions, so thanks.
Thank you very much.
Thank you. Thank you very much.
Thank you very much. Very nice talk. And well, to the audience and also the speaker, of course, see you next week when we continue our seminar. Have a nice day. Bye-bye.
Bye.
Bye-bye. Thank you very much.
Thank you.